For today's notes, you will need in class 61, double check that says part number 3, area of polygons on the top. All right, we are continuing our work on standard 14, and the focus today is on a shape called a regular polygon. We're going to start with the definition. A regular polygon is a polygon. That means that it has straight sides and corners, and it's closed. That has all congruent sides and all congruent angles. You can write out the word congruent if you prefer. And so if we take a sneak peek down below to this picture, this is an example of a regular polygon if all 5 of these sides are identical and all 5 of these interior angles at the corner are identical. Okay? Regular polygons have what's called a center, which is a point that is equidistant or equal distances, if you want to write that as 2 words, from all of the vertices. The vertices are the corners of the shape. And so when we're looking again at that picture down below, this would be the center point. It's going to be an equal distance from every single one of these corners. Okay? The radius is actually that distance. So we used radius when we were learning about area of circles, but a radius also exists in these regular polygons when we travel from the center of the shape out to the vertex. So in this picture down below, this solid line or this dashed line are both what we would consider radii. They're each a radius of that shape. And then there would be 3 more that we could draw in if we included all of them. Next up is something called the apothem or the apothem. I've heard people say it both ways. That's going to be the distance from that center point still, but instead of traveling to the vertex, we're going to travel to the midpoint of a side. And when we do that, it forms a right angle with that side. That happens because if we're going from the center to the midpoint of a side, it forces these 2 pieces to be congruent to each other. We already know that our radii are congruent, and then we could use reflexive property to call that side congruent to itself. So it forces these 2 triangles to be congruent triangles, which means these 2 angles have to be congruent angles, so therefore it's a right angle. Okay, so in our picture, this would be the apothem or the apothem. We label that with a lowercase a. Last up, in terms of the parts of these regular polygons, we have what's called a central angle. That's again an angle that's formed at the center of the regular polygon by 2 consecutive radii. So in this picture, this entire angle right here, so in this little triangle that has solid sides but extended all the way back to that radius right there, that's the central angle. So that central angle I'm just going to label by kind of drawing out of that section with a theta. But that whole angle right there is what we're talking about. Okay. For our area of regular polygon problems, you're going to need to know the names of 6 different regular polygons. They are listed right here. So they're named based on the number of sides that they have. Some of these are going to be familiar because you've learned about them in the past, and others might be new. So if a regular polygon has 5 sides, like this one that we've been working on down here, it's called a pentagon. If it has 6 sides, we call it a hexagon. 7-sided regular polygons are called heptagons, H-E-P-T. 8-sided regular polygons are like stop signs. Those are octagons. A 9-sided regular polygon is called a nonagon, and then a 10-sided regular polygon is called a decagon. So what will happen in the problems that you're asked to do in your homework and on your assessments is that there won't be a picture given to you. It will just be described in words, the type of regular polygon you're dealing with. So you're going to need to know that if they say heptagon, that means 7 sides. Or if they say nonagon, it means 9 sides. So you'll need to remember those 6 names for regular polygons. All right, moving into the actual focus for today. Our goal is going to be to find the area of these shapes. And so what happens is we rely on triangles to help us do that. If you look at this situation that we have drawn in this picture, we have a little triangle here. I'm going to actually go ahead and highlight it so we can focus in on it a little bit more carefully. That repeats itself over and over and over in this regular polygon. There are 2 of these per side that are identical. So if we could find the area of this little triangle, we would be able to multiply that by something to fill up that entire regular polygon. So what we notice, if we're thinking about the area of this triangle, is that we have something available to use as its height. That's the apothem we just marked in. And then down here would be the base of this little triangle. And that is going to be half of this side length. So for this little triangle, we would have 1/2 times the apothem times half the side. But then what happens is we multiply by a certain number to fill up the rest of that shape. And a shortcut of doing that is actually to keep the 1/2 and the apothem. So that's the 1/2 and the height. But then the base is really this entire distance all the way around by the time you put all those triangles together. So we might write that as apothem times perimeter divided by 2. Perimeter is the distance all the way around that shape, which puts all those bases together. Or you could write that with a 1/2 out front and then the apothem times the perimeter. Or sometimes what people do, since A represents the apothem and P represents the perimeter, is they substitute in how we actually find the perimeter. So perimeter is found by taking the number of sides and multiplying by the side length. So this N would represent the number of sides in the polygon, and this S would represent the side length. And so sometimes this formula is written either with the 2 on the bottom or the 1/2 in front. That part doesn't really matter, but it's written as A times N times S over 2. Apothem times number of sides times side length divided by 2. Or you could pull that 1/2 and it would be 1/2 A times N times S. This formula right here that I'm going to circle is the one that's on your assessment resource card that you get to use during your assessments, but all of these others are equivalent to that. If you prefer one of those, that's fine. You just need to remember it for yourself when it comes to taking your assessment. Okay, let's go ahead and practice some of that vocabulary, and then when we get to the next page, we'll practice actually using that area formula. So what we're going to do for each of these problems is first and foremost, we're going to draw and label a radius and an apothem. So all of those are connected to the center of the shape. The radius is going to be connected to the vertex, so that would be an example right there of a radius. The apothem, remember, is connected to the midpoint of the side. So that would be the apothem. It makes a right angle, so we're going to draw that in and then mark that those 2 segments are congruent. All right, they also want us to show a central angle and then to shade or highlight the attached side length. So if we are showing a central angle, we need to make sure that we have 2 radii back to back. So if I'm going to do that, I might actually just hop over here and put 1 more radius in and try to reuse this one as my second. That angle right there would be the central angle. Remember, we can label that with a theta if we'd like. And then if we're going to shade or highlight the attached side, that would be this whole entire side right there between those 2 vertices. All right, last but not least, we're filling in the blanks for the polygon name and the central angle measure. So this polygon name is related to the number of sides. So if we start counting, we've got 1, 2, 3, 4, 5, 6, 7, 8 sides. 8-sided polygons are octagons. And since there's one central angle attached to each of those 8 sides, all together they would make a full rotation of 360 degrees, but that's going to get split up into 8 equal central angles. So 360 divided by 8 will give me that central angle measure for this octagon. That will be 45 degrees. All right, same tasks for part B. We're going to start at that center and draw in a radius to one of the vertices. Label that with an R. Back to that same center point, but down to the midpoint of a side to show the apothem. We're going to get a central angle here. Again, I'm going to reuse that radius, but then use the other one right next door to finish out that central angle. And then the side attached to my central angle would be right there. This polygon has 1, 2, 3, 4, 5, 6 sides, so it is a hexagon. And again, it's going to have 6 central angles rotating around the center of that shape, so we'll do 360 divided by 6 to figure out the measure of that central angle is 60 degrees. All right, 2 to go. This polygon has a lot of sides, but we're going to start the same way. Find that center, connect that to a corner vertex to find the radius. Back to the center, but connected to the midpoint of the side with a right angle is the apothem. We're going to take this radius and the one right next door to mark our central angle. Then this would be the highlighted or shaded side connected to that. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides this time, which tells us that this regular polygon is a decagon. One central angle attached to each side means we're doing 360 divided by 10 this time. And our central angle will turn out to be 36 degrees in a decagon. All right, final example, practicing the radius drawn from the center to the vertex, the apothem drawn with a right angle from the center to the midpoint of the side. A central angle is going to take 2 radii next to each other, and then it connects to an entire side of the triangle there. This regular polygon has 7 sides, so this one's called a heptagon. And heptagons are a little bit bizarre because when we take 360 and we divide by 7, that does not turn out to be a nice number of degrees that's exact like all of the others. So we're going to end up with a decimal here. Sorry, my calculator is not cooperating. There we go. So that is our central angle. We're just going to round it to a couple of decimal places. Pay attention in class to how your teacher tells you to round it. But for today, I'm just going to call it 51.43 degrees. That second decimal place would round up to be a 3, thanks to that 8 in the third position. But that is an approximate central angle, not an exact one. Unfortunately, that's the best we can do with a heptagon, unless we just kept it as 360 divided by 7 in fraction form. All right, go ahead and flip the page, and we will continue on and see if we can see how this actual formula will be used to find area. All right, we've got 2 helpful reminders from previous standards that are going to help us with our goal of finding the area of regular polygons. So first and foremost, we've got a triangle sitting here that has a 30-degree angle and a 90-degree angle. That means that our third corner would be 60 degrees if we filled it in. And I'm hopeful that we will remember our relationships from the 30, 60, 90 triangles. That side across from the 30 is your shortest leg. The one across from the 90 is going to be 2 of those shortest legs, 2L. And then the one across from the 60 is going to be L times root 3. So we'll be using that relationship sometimes. And then the other relationship we need to remember is our sine, cosine, and tangent ratios. So if we have an angle and we're trying to do sine of that angle, that involves the opposite side and the hypotenuse. Cosine involves the adjacent side and the hypotenuse. And then tangent involves the opposite side and the adjacent. So we'll be using those trigonometric ratios to help us with these problems as well. Okay, here we go. Problem number 1 through 6 are asking us to find the area of a regular polygon in 6 different situations. So for every single one of these, when they ask you for the area of the regular pentagon or hexagon, I would recommend that you do 2 things at the very beginning. Fill in how many sides that shape has right next to that name. So pentagons have 5 sides. And then we know we're looking for area, so I'm going to write myself a game plan here. Area is going to be apothem times perimeter over 2. I'm going to use the version of the formula that's on your assessment resource card. After you do that, I'm going to draw the little triangle that we were drawing on the previous side of the page with a little bit of adjustments. So I'm not going to draw the whole pentagon because sometimes drawing hexagons is really tricky for people. I'm going to draw that apothem, one side of the pentagon. Okay, so that right angle is there, and we know that these are equal. And then this is that radius. Okay, so for this first problem, I'm going to go ahead and label those. But for the others, we're just going to try to remember in our mind what each of those 3 sides represent. Okay. So then as I continue to read and they tell me that this pentagon has a side length of 6 feet, that means this whole entire segment is equal to 6. Well, the most helpful thing for me to do with that is to use these 2 congruent marks to remind myself that that 6 is going to get split in half, 3 and 3. And the reason why that's important is because if that apothem is missing, I need it for my formula. I'm going to use this right triangle with one of these 2 reminder facts, hopefully, to help track down that missing apothem value. I do not need the radius, so the only reason I labeled that on my picture was to remind you where it's located. Maybe a problem later on will tell us the radius, but for right now, that one is not needed, so that's not going to be our focus. So I have 2 things I need to find. I need to find the apothem and I need to find the perimeter. If I'm thinking about the apothem, I need another clue about this triangle because as it is standing right now, I don't have enough information to be able to find it. So let's put that other radius on the picture that we saw on the other side. And remember that this entire angle is that central angle that we were working on finding. So if I do 360 divided by 5, the number of sides, that would be the entire central angle between radius and radius. My focus, though, is on this little triangle that only takes up half of that space. So that central angle is helpful, but it's too big. So I need to take that central angle and cut it in half to be able to have information about this particular triangle that I'm working on. So 36 degrees is going to be the way that I do that. You can take care of that all at once by actually dividing by twice the number of angles, double the number of sides, double the number of angles, or you can find the central angle and then divide it in half. Okay, so now that we've got this all set up, we need to decide, are we in a situation where this L root 3, 2L stuff will help us, or are we in a situation where sine, cosine, or tangent will help us? Since I have 36 degrees, this has got to be a sine, cosine, tangent problem. So if that's my reference angle, over on the other side of the shape would be opposite, and that apothem is my adjacent side. So to track that down, I'm going to need a tangent equation where 36 degrees is the reference angle, and the opposite side is 3, while the adjacent side is A, the apothem I'm looking for. Since that variable is over on the fraction side, this is a review of standard 13. We would multiply both sides by that A. And then to isolate that A value, we would come back in and need to divide both sides by the tangent of 36. So this apothem is going to be a rounded value. However, I'm going to keep it on my calculator because I want to try to avoid rounding until the very, very ends of these problems. 3 divided by tangent of 36 is 4.13 if I'm rounding, but I'm just going to let that number sit there for right now because I'm going to be able to use my calculator to keep that nice and exact for my area calculation later on. Okay, so I've got the apothem tracked down now. That part's taken care of. Next up, I need the P. Remember, that stands for perimeter. Perimeter is the distance all the way around the pentagon. So even though I didn't draw the whole shape, I reminded myself that there were 5 sides, and each side was 6 feet long. So that means my perimeter is just 5 times 6, or 30. Now that I've got the apothem and I've got the perimeter, I'm ready to plug it all in and finish this one out. So that apothem is going to be 4.13, but remember that was rounded. So I'm going to put some decimal or some dots there to show that I've got that whole number still on my calculator. The perimeter is 30, and then I'm going to divide that by 2. So since this apothem value is still sitting here nice and exact, I'm going to make the calculator use that whole entire thing. I'm going to multiply that by my 30 for perimeter, and then divide that whole thing right away by 2, which means I'm avoiding my rounding until the very, very, very end of this problem. So the area of this regular pentagon is 61.94. That 3 will round up. 61.94 square feet, since that was the label they gave me for that original side length. All right, first example done. Ready to move on to the next one. We do the same thing every single time. There's just a difference in terms of the number we're given and the angle that forms that central angle. So this time we start reading. We're going to find the exact area this time instead of rounding of a regular hexagon. Hexagons have 6 sides, and we're given a radius this time. So first things first, my goal is area of a regular polygon. So AP over 2 is the goal. I'm going to set up my apothem, which I do not know. My radius, which I do know, that's 12. My side length for the hexagon, which is cut in half. And then I'm going to start working on finding that angle at the top. So if we're in hexagon mode, the central angle would be 360 divided by 6. But remember, this is only half of that central angle, so we're going to need to divide that by 2. Now I'm really happy because I see a 30 there, which means I'm going to be able to use this 30, 60, 90 special right triangle stuff, which is actually why we're allowed to get an exact answer on this one. So my side across from 30 is the L. My hypotenuse is the 2L. And then the one across from the 60 is the L root 3. Right there, if I divide by 2, that tells me that 6 is L. And if I plug it in, that tells me that 6 root 3 is my apothem. We've got the A already tracked down, so we could go ahead and plug that part in. The apothem turned out to be 6 root 3. We just need to find the perimeter, and then we'll be able to calculate our area. So remember, perimeter is supposed to be the number of sides, which is 6, times the side length. Well, that side length, remember, is the whole side, not just the part of the triangle. So if that part right there is 6, that means this part is also 6, and 2 6's put together gives me a side length of 12. So perimeter is going to be 6 sides times a length of 12, or 72. We'll go ahead and plug that in. And if our goal is to keep our answer nice and exact, we need to avoid that root 3 when we go to the calculator. So we'll do 6 times 72 to find the numerator. That can get divided by 2 probably to stay nice and exact. So 216 takes care of all of the numbers that are outside of the root. And then we'll just attach that root 3 onto our answer. do a quick check, and square inches would be our area. All right, onward we go to example 3. This time we're dealing with the area of a regular octagon. So that means we're going to end up dealing with 8 sides. But our area formula doesn't change. Anytime it's a regular polygon of any type, apothem times perimeter divided by 2 is the goal. My apothem goes straight down, and they actually tell me this time around that that's 22. I don't know my radius, but that's okay. I've got my side set up here with my right angle and those 2 pieces equal. I need to find that half central angle up there. So the alternative to finding the whole central angle and then dividing it by 2 is to actually take 360 and instead of dividing by 8, just divide by twice as much. So 16 would go straight to that partial central angle. That's going to be a decimal, but it's an exact decimal. So this angle, kind of hard to squeeze in there, so I'm just going to attach it to that little arc, is 22.5 degrees. That tells me that I'm not in special right triangle mode, so I'm going to need to use sine, cosine, or tangent. I already have the apothem, so the A is 22. Perimeter is what I'm on the lookout for. So if we think about that whole perimeter thing, I need my number of sides, which I know, but then I need to multiply by the length of a side. So that means what I'm really searching for is that x at the bottom of the triangle, because I could use that x to help me figure out what that whole entire side length is equal to. So if we're set up at this reference angle of 22.5, that means I'm looking for my opposite side, but I know my adjacent. We are going to use tangent. Sorry, the bell rang, so if I already said that, I apologize. Opposite and adjacent means tangent of 22.5, our reference angle, will equal x over 22. Our variable is still over in that fraction, so we're going to multiply both sides by the denominator of the fraction, which actually leaves that x by itself already. So we're headed to the calculator to do 22 times tangent of 22.5, which is approximately 9.11. However, let's keep in mind we want to try to avoid rounding until the end. So I'm going to set that off to the side. I'm going to write down that this is close to 9.11, but then I'm going to think about my goal of perimeter. Perimeter is not just x. Perimeter, there's a bell again, sorry, is the number of sides times the side length. And that side length is made out of 2 of these x's back to back. So on my calculator, I'm going to go ahead and multiply that by 2. Now I have a side length. So that number is what I would put into this perimeter calculation. But I'm going to keep that nice and exact and go ahead and also multiply, without any rounding happening, by 8. So my perimeter is now close to 145.80, but there are still a bunch of decimals attached to that. So since I've already got my area formula set up, next up, I'm going to take that perimeter and plug it in. It's already on my calculator, so to avoid rounding, I'm going to go take it and multiply it by 22, and then divide it by 2. So I've carried that decimal all the way through all of those calculations without doing any rounding to get my most exact answer possible for the area of this octagon. So area now is going to be rounded to 2 decimal places, which means it's 1,603.83. I notice that's really close to rounding up, so I imagine that if we had not been careful with our rounding error, we might have gotten a different answer out of that. So the goal is to try to avoid rounding till the very end of the problem by using your calculator carefully. Units on this one is centimeters, so that's going to be square centimeters. Okay, 3 down and 3 to go. For question number 4, we're dealing with a regular nonagon. Nonagons have 9 sides. We're still in the area of a regular polygon mode, so my formula is going to be AP over 2. Looks to me like I need to find my apothem. I don't know the radius, but they have told me this side length is 4. So I'm going to go ahead and split that up 2 and 2 right away and try to find that half central angle at the top by doing 360 divided by 18, double the number of sides. So this angle at the top is going to be 20 degrees, which tells me that I'm going to be in sine, cosine, tangent mode again, because that's not a 30 or a 60 or a 45. So I've got opposite available, and I'm looking for adjacent, since I need the apothem for my formula. Tangent seems pretty popular today. This time the reference angle is 20. Opposite is 2, adjacent is A. The variable is in that fraction, so we're going to multiply by the denominator, which moves that apothem value over to be multiplied by tangent of 20. So to finish out that apothem calculation, we're going to need to do 2 divided by the tangent of 20. That is definitely going to give me a decimal, but I'm just going to let that sit on my calculator. I'm going to write down 5.49 with some dots to remind me that that's on my calculator. And that's going to be my value for the apothem part of this area calculation. So now that all that's left for me to track down is the perimeter part. So perimeter is going to be the number of sides, 9, times the side length of 4, which gives me a 36 for that perimeter number. So if I come back to that apothem that's still sitting on my calculator, multiplying by 36 and then dividing by 2 should finish out the area calculation and give us 98.91 if we round that to 2 decimal places. Square centimeters again, thanks to that label given at the beginning. Number 5, find the area of a regular decagon, 10 sides in a decagon. And oh boy, I see that this one has a radius given to us, which is going to mean this is going to be the trickiest problem we've done the whole time. So here's my apothem. That's a mystery. The radius is 14, so this goes on that side. And then if I'm finding that central angle up top, I'm going to divide by double the number of sides so that I can go straight to that angle, being 18. Now here's the problem. If we're looking to find the area of this shape, we need the apothem and we need the perimeter. And in order to find that perimeter, I'm going to need the number of sides times the side length, but I don't have the side length. And I don't have a part of the side length. So I'm going to need to find that x, which will match this, which will then be used as that side length that I'm using. On top of that, I don't have the a. So there are 2 missing things in this problem. With a reference angle of 18, this would be opposite, this would be adjacent, and across from the 90 for the first time on this page, I have the hypotenuse. So we're going to have to deal with one problem at a time. I'm going to go for the apothem first because I don't need to do any more math with that. So if I'm looking for the apothem, I've got adjacent and hypotenuse available. That means cosine is going to be the correct setup. To solve that, we're going to multiply both sides by 14, which means my apothem value is going to be 14 cosine of 18. Now, if you're really good at using your calculator, you might be able to leave this on here and do all the calculations for the x as well. But I have a feeling most of us, this is going to disappear. So because I have more to do and I don't want to end up with rounding error, I'm going to write a bunch of extra decimal places. So I'm going to go to 5. So 13.31479. And that's going to be my workaround for not being able to keep that apothem in my calculator to use later for the area calculation. All right, onward we go to the next phase of this problem. That's to track down the x. So I'm going to ignore that apothem there, which means I've got an opposite and a hypotenuse to focus on now. So we're going to use a sine equation this time with our reference angle, where x is the opposite and 14 is the adjacent. Still multiply both sides by 14. So that little x is going to be 14 sine 18. 4.32 with a whole bunch of other decimal places. Now remember that x is only half of a side, so we multiply by 2 right away to get a whole side length of like 8.65 with a bunch of decimal places. That is what's going to get multiplied down here by 10 to turn into perimeter. So again, I'm trying to keep that rounded answer from happening for as long as possible. So 86.52 with a bunch of decimal places. And now I'm going to go ahead and plug in what I have, keeping in mind that that perimeter is still sitting on my calculator. So area is this apothem that I've kind of lost on my calculator, but I wrote down a bunch of decimal places for. I'm going to run into this next box. Times the perimeter, which is still on my calculator, divided by 2. So we're going to take that perimeter, done. We're going to multiply that by what we wrote down before with all those decimal places for something super close to the apothem. And then we're going to divide that by 2 to get our best answer for the area of this decagon. 576.03 if we round to 2 decimal places. And again, centimeters for this problem. So centimeters squared. That's going to be about as hard as it gets for these because we were missing both of the pieces that we needed for our area formula. All right, last but not least, we're dealing with a regular heptagon, so 7 sides. They do give us the apothem this time, so 10 inches is going to go on that perpendicular right angle side of this shape. Remember, this is the midpoint, so those two are equal. We are finding area still, so area will be AP over 2. I do have the apothem already, so I could plug that 10 in. I just need to work on tracking down that perimeter. So if I think about perimeter, I need that whole side so that I can take 7 times that whole side to figure out the perimeter. That means I'm going to need this angle at the top so that I can find this half side and then turn it into a whole side. For a heptagon, there are 7 sides, so I'm going to divide 360 by double that number to figure out that half central angle. And unfortunately, that is not a nice value. So this is the first time that angle we're using has been a decimal. We're going to keep at least 2 decimal places on that angle. So I'm going to call that angle 25.71 degrees. It's going to be hard to fit in here, 25.71 degrees. So that angle tells me I need to use trig. Opposite and adjacent are available. So tangent of 25.71 will equal the opposite, x, over the adjacent of 10. Multiply both sides by 10 to get that x by itself. And so what we're doing, if you can use your calculator carefully, you can actually get that whole angle plugged in. We need to do 10 tangent of that whole thing. So most of your calculators, that negative key, if you press the second button first, it will plug that whole previous answer in for you. So now that's doing 10 tangent of that whole entire decimal without me needing to type it in. So that gives me the side, x. To get that to be an actual side for the heptagon, we need to double it. So now we're in actual side mode at 9.63 with a bunch of decimals. So to turn that into perimeter, we need to multiply it by 7. So my perimeter now is 67.42 with a bunch of decimals. I can pop over here and plug that in, which means I can take that number that's already sitting on my calculator, multiply it by 10, and divide it by 2 to finish out this area calculation. Get 337.10 square inches. All right. Thanks for learning about area of regular polygons today. We will see you back in class.